My topic is a breast cancer convolutional neural network in order to determine if a tumor biopsy is malignant or not. My name is Anne Strange, and a little bit about me. I love data. I love the Colorado outdoor lifestyle. I have a background in computer science, but I'm looking to pivot towards biotech because cancer is something that has affected people close to me, and I'm excited about what the recent technology might be able to do. Let's talk about breast cancer. US women have a 1 in 8 chance of getting breast cancer in their lifetime. It's the second leading cause of cancer death in women, and early detection still relies a lot on manual processes by pathologists. My goal is to use a CNN to see how I can do at predicting, maybe helping that process. Let's first take a look at what a pathologist might look for in the slides. We have some examples on the left of malignant slides, and without being a pathologist, I can tell you that these large nuclei are an indicator of malignancy, as well as the density and the cell division going on here. We also have irregular and aggressive shapes. The cells are not sticking to their tissue types, as we could see over here in the benign examples. There are lumps, but they're orderly, more sparse. And if we see some aggressive looking cells, they're sticking to their tissue type. This might be a duct right here. How to set up a CNN. Here's a model that I used based on the AlexNet model, where the images come in from the left, go through a convolutional layer to capture the features. It then goes through max pooling layer, which helps reduce dimensionality and helps it generalize rather than just memorize each pixel. At the end, we have our predictions, benign or malignant, which are corrected for how wrong they are, and information sent back into the model to help it do better the next time. Repeat many times, and it turns into it eventually gradually learns, in quotation marks. What really helps the model is having as much data as possible. So I did ×10 on my data by using data augmentation. I wanted the model to understand that what's important in each slide is the pattern, not where it specifically is on the slide. So I rotated it, flipped it, jiggled it around to help train the model. The result of my model was a recall score of 95%, which is the fraction of actually malignant cases that are predicted positive. This is a trade-off. It only achieved 82% accuracy. So the cost is to false positives, where we have some people that are actually benign getting predicted as malignant. So perhaps this is not taking the place of a pathologist, but a tool in their tool belt. We might want it to flag extra likely malignant cases for earlier review. Let's take a look at some classifications from the model. We have on the left the malignant cases that were properly classified. And we do see the patterns we were talking about with large, dense cell structures, irregularity, and aggressiveness. On the benign side, we have what we expected, some sparseness and regular circles. But it does appear that there's a reliance on pinkness for the malignant predictions. And this is something that may be a limitation of the model because we know there's a lot of stain variation coming from the lab and the pathologists that should not be too strongly weighed as a predictor for malignancy. So that's something we have to be careful about. Here's some incorrect predictions. This one was incorrectly classified as malignant, but in fact it's benign. And the reason might be that these cells down here look like it's cell division, but perhaps not. Also, there's some angry looking cells, but they're contained in their tissue type. We have one incorrectly classified as benign. Perhaps it's because these look a lot like the benign slides we saw earlier, but we can see trouble brewing in the top right corner. That could be the reason. Obviously, the model is not perfect. It has some limitations. It would be great to come back and as next steps, get some additional data and neutralize for stain variation. It would also be great to try a more recent model and try transfer learning. There's been some success in the field with those. And a deconvolutional net helps illustrate the feature patterns that might explain why it's coming up with the answers. That would be really cool to try. In conclusion, I really enjoyed this project, and here's my tech stack, and I'll open it up for questions.